we know that the common subsequence is a sequence that is present within the strings of V and W. So it means that every common subsequence corresponds to an alignment with no mismatches, and this can be obtained just simply by removing the diagonals that are at the position in which there is a mismatch, and we will retain the diagonals only at positions that are identical. It means that at that positions the alphabets that are present in both V and W strings that are identical. And after removing the diagonals, we will get a specific figure that we will see in the next slide. So we will get this type of graph, and we can see here that we have retained only those diagonals. For example, we consider this diagonal, and if we see the position of this diagonal, we can see at both positions T is present. If we consider this diagonal, we can see here at both positions A is present. So we will consider only those diagonals that are identical. So at random we can consider all of these. So we will only retain these diagonals. So after retaining these diagonals, we will come up with the sequence that is a subsequence at and is present in both of the strings, that is V and W. So the relation between the Manhattan-Tourist problem and the longest common subsequence is further illustrated by showing that these two problems leads to a very similar recurrence. So if we define the Sij, any vertex in the graph, to be the length of the longest common subsequence between V1 up to the value of Vi, in which the I prefix of V and W1 to Wj, the J prefix of W. So it is clearly indicates that the Si0 and S0j is equal to 0. And for all of these, the value should be 1 should be less than or equal to I, and I should be less than or equal to N. And similarly, I should be less than or equal to J, and J should be less than or equal to M. And these M and N are the characters within the V and W strings. Similarly, Sij satisfy the following recurrence. So we have seen that both the Manhattan-Tourist problem and the longest common subsequence has the same recurrence values and same recurrence solution for this problem. So we can see that we have already find the recurrence problem for Manhattan problem, and now we will see the recurrence problem for the added graph, in which we have calculated the longest common subsequence. So the value will be, we have to calculate Sij, and we have to see the maximum value from these three equations. So the first is Si minus 1j, Sij minus 1, and Si minus 1j minus 1. So these two we have already calculated for the Manhattan-Tourist problem. And the third is this one, plus 1 if V and W strings, if they are equal or identical. So the value that we will get from these three, we will select the value that have the maximum score. So the first term, that is this one, it represents when Vi is not present in the longest common subsequence of the I prefix of V and J prefix of W. That is, if it is not present in the V, it means that there is a deletion of one alphabet in the V matrix. And this second mathematical equation denotes that when Wj is not present in this longest common subsequence, and it means that it is an insertion within a W string. And the third representation is that when both V and Vj are present in the LCS. So it means that in this alphabet is missing from the V string. In this one, the alphabet is missing in the W string. And this equation is when the alphabet are identical at a particular position in both V and W strings. Similarly, we can see that this is the same equation. We have seen same, but the only we have added a 0 after this equation and this equation. Otherwise, the equation is almost identical. So why we added the 0 is the recurrence for the LCS computation is like the recurrence given at the, we have already seen in the Manhattan problem. And if we want to build a particularly difficult version of this Manhattan problem and gave the horizontal and vertical edges weight of 0 that we have assigned here, and set the weights of diagonals, that is, we know that whenever we use the diagonal, it means that it is a matching. And then edges equal to +1. Here we can see this is a +1 edges as it is indicated in this figure. So we can add the 0 and +1 at the edges, and we will get the subsequences that are present in both the V and the W strings. So we can use the S to represent dynamic programming table and the data structure that we use to fill the dynamic programming recurrence. So the length of the LCS between the V and W can be read from the elements M and N of the dynamic programming table, but to reconstruct the LCS from the dynamic programming table, we can keep some additional information about which of the three quantities. And one is the Sj-1, I-1j, second is the Sij-1 or the S1 I-1 j-1 plus 1, and it corresponds to the maximum of the recurrence for Sij we have seen in the previous slide.